Namaste and welcome to yet another lecture on the course on linear algebra through geometry. In the last class we looked at real symmetric matrices, properties of real symmetric matrices, and in the 2 by 2 case at least we proved that the real symmetric matrix has real eigenvalues, and we also looked at the product A transpose A and A transpose being symmetric matrices, and we also said that this real symmetric matrices find a lot of applications in, especially in the domains of all ML, data science and other things. And typically we look at the variance covariance matrix where we find this real symmetric matrix to be the variance covariance matrix is actually a real symmetric matrix. There is another important property of the real symmetric matrix which is concerned with the eigenvectors of these class of matrices, the eigenvectors associated with distinct eigenvalues of the class of these matrices, and in fact that is what is going to give us insight into what is this real symmetric matrix trying to do when it tries to transform a vector, and that will be the crux of our lecture for the day, right. So, we will look at the eigenvectors associated with distinct eigenvalues of a real symmetric matrix, and then we will go further. We will take the help of an orthogonal matrix, we will try to do something over there, and then get back to see what is the effect of a real symmetric matrix on a given vector. How does a vector get transformed to another vector by a real symmetric matrix, let us say with distinct eigenvalues, and that is what we are going to look at in this lecture. In the next lecture we will look at the idea of quadratic forms, and we will again see like where do we apply this quadratic forms and all those stuff. We will look at that will be the crux of the next couple of lectures. We will also try to generalize the idea of the eigenvalues of real symmetric matrix being real. We just took the 2 by 2 case last time, and then we proved that it is going to be real, the eigenvalues are going to be real values. We will look at that for any n by n in the next lecture, and then start with quadratic forms. In this lecture the focus is on the eigenvectors corresponding to distinct eigenvalues of a real symmetric matrix, right. Most of us, when we say Ax is equal to B, suppose if A is an m by n real matrix, we know that the m by n real matrix, basically a transformation, is going to take an n component vector and transform it to an m component vector. Suppose I take A to be an n by n matrix, it is going to take an n component vector, a vector in Rn, and then it is going to transform this vector in Rn to another vector in Rn itself. Now, most of the times mathematically we understand like what happens, like how do we get the individual component of the resultant vector, which is basically the first row into the column, the vector corresponding to the x vector, multiplying the each component and then adding it and then get the first component of the b vector and so on. Mathematically we understand that, but I mean what is the geometry, what is actually happening there, that insight is not something which we really bother about, or which we really which we tend to lose sight of, because most of the times the numbers, when we get the numbers, we know that okay, if I do this A into x, I am going to get that B, the matter ends there. But if we get more insight into what is actually happening, like how does this real symmetric matrix A transform a vector x to another vector B, and that is very interesting. And in fact what we will see is this would form what would you call as, this idea of whatever that we are going to look at now is what is going to be taken even in the case of singular value decomposition, for which in which case we are going to look at say let us say a rectangular matrix, which could be a tall matrix or a wide matrix, for which eigen decomposition is not possible. But we are going to exploit the same idea that we are going to use here. We will be exploiting that idea there in our A m by n. So, let us get on to our real symmetric matrix case. Okay. The first thing is, as always, we will take the simple example, the case of 2 1 1 2 matrix, which is a real matrix. We have already worked this out in our earlier lecture on 2 by 2. So, let us look at this matrix A, which is 2 1 1 2. So, A here is real and symmetric, right. Now, we know that the eigenvalues for this are lambda 1 is equal to 3 and the corresponding eigenvector, which is nothing but 1 1. Lambda 2 was equal to 1 and the corresponding eigenvector was 1 minus 1. Now, let us take a closer look at these two vectors, eigenvector 1 and eigenvector 2. We see something interesting here. Let us take the dot product of this 1 1. Basically, let us take the dot product of EV1 with EV2, EV1 dot EV2. What is that? We have 1 1 dot product with 1 minus 1. We already know what it is 1 1 eigenvector 1, the transpose of that vector, and eigenvector 2, this is going to be 0. That is interesting. If the dot product of two vectors is 0, what is it that we can tell about the two vectors? We know that if the dot product of two vectors is 0, the vectors are going to be orthogonal. So, this means eigenvector 1 is orthogonal to eigenvector 2. Now, it is interesting, when if we take a different matrix, which is if we take a matrix which is not let us say a symmetric matrix, we may not have this property. But what we see here is, for a symmetric matrix, we find that the eigenvectors associated with distinct eigenvalues are orthogonal to each other. That is something interesting. Now, let us take this matrix P. We know what when we wanted to do the we wanted to express A as PDP inverse. Let us take this matrix P, which is basically 1 1 and 1 minus 1. Our D matrix is basically 3 0 0 1. This is what it is going to be, right. Now, I want to do a small interesting thing here. What I want to do is, I want to look at I want to have a closer look at eigenvector 1 and eigenvector 2. What is the length of eigenvector 1? Length of eigenvector 1 1 1 is basically 2. This is basically root 2. Yeah. So, now what I am going to do is, I am going to get a unit vector out of this. So, I am going to let us say EV1 cap is nothing but 1 by root 2 and 1 by root 2. And what is the length of this eigenvector 2? I am going to get an eigenvector 2 cap, which is nothing but again 1 by root 2 minus 1 by root 2, right. So, let me form this matrix R, which is going to contain the unit vector. Now, what we have is, the matrix P basically had orthogonal eigenvectors. What I am doing is, I am now constructing a matrix R, wherein which the vectors are going to be not just orthogonal, but they are going to be orthonormal. That means, the vectors are going to be of unit length and they are going to be orthogonal to each other. So, I am going to write this as 1 by root 2, 1 by root 2, 1 by root 2 minus 1 by root 2. This is what I have. Now I want to find out the inverse of this matrix. So what is R inverse? What is R inverse? When we did the what would you call, when we did the rotation matrix, when we looked at the rotation matrix in 2 dimension, we found that if you want to rotate a vector by an angle theta in the counterclockwise direction, we had this matrix, if you recall, we had this matrix R theta, which was basically cos theta sin theta minus sin theta cos theta. This was basically rotation in the counterclockwise direction. Now I wanted to look at, I rotate a vector by an angle theta in the counterclockwise direction, I reach another point. Now I want to come from that particular point back to the original place, which means now I have to rotate the vector by a counterclockwise direction in the clockwise direction by an angle theta. Is that right? What did we do? We had R theta to be the rotation, the matrix which rotates any vector by an angle theta in the counterclockwise direction. I have reached my destination by rotating this vector by, let us say, an angle theta. I want to come back to this original position, which means how I have to rotate the same vector by an angle theta in the clockwise direction, which means I have to come back by minus theta. So what was R minus theta? R minus theta was basically this. It was cos of minus theta, sin of minus theta, minus sin of minus theta, and cos of minus theta. So what was this R minus theta doing? R minus theta, the vector R minus theta, the matrix R minus theta was basically trying to undo the effect of the matrix R theta. That means R minus theta is going to be the inverse of that operation that we did, which is the R theta operation. So R minus theta, we are going to see this is nothing but cos theta sin theta minus sin theta cos theta. So R minus theta is nothing but R theta inverse, and that is exactly equal to R theta transpose, right. It is equal to R theta transpose. If you look at the length of this particular column vector cos theta sin theta, the length is 1. If you look at the length of this column vector, the length is 1, and if you look at the dot product of these two vectors as such, what we see is the dot product of the two vectors is basically 0, which means these two vectors are orthogonal to each other. That means a matrix which has orthogonal columns and each column has a length 1, the length of each column vector is 1, is called as an orthogonal matrix, and the inverse of an orthogonal matrix is basically its transpose itself, right. So what is going to look at, so we are going to write this. So what is R theta inverse in this case? R theta inverse, I mean R inverse in our case, whatever that we are looking at right now, R inverse is basically the transpose of this matrix. What is the transpose of this matrix? The transpose is 1 by root 2, 1 by root 2, 1 by root 2 minus 1 by root 2. Let us see if R inverse is equal to R transpose. Let us try to look at R transpose into R and see whether it is identity matrix. R transpose is 1 by root 2, 1 by root 2, 1 by root 2 minus 1 by root 2. R is nothing but the same thing, 1 by root 2, 1 by root 2, 1 by root 2 minus 1 by root 2. So what do we get? We basically get 1 by root 2 into 1 by root 2 is 1 by 2 plus 1 by 2, which is 1. 1 by root 2 into 1 by root 2 is 1 by 2 minus 1 by root 2 into minus 1 by root 2 0. So similarly you get this 1 by root 2 into 1 by root 2 is half minus half, which is 0, then 1 by root 2 into 1 by root 2 half plus half, which is 1. So we see that R transpose R is identity matrix. So what is it that we found? We found that if you make the columns of this P matrix that we get of the real symmetric matrix. Suppose we have a real symmetric matrix A whose eigenvalues are distinct, we figured out that the eigenvectors in that case will be orthogonal to each other. Now what you do is you make them as orthonormal vectors, divide each of those eigenvectors by the length, you get a matrix R. Now what you see is, instead of expressing the matrix A is equal to P D P inverse, now it is becoming R D R transpose, right, because P inverse would equally be, it will be equal to R transpose. You have your orthogonal matrix R, therefore the transpose of the matrix is going to be the inverse of the matrix, right. So let us make this quick definition of orthogonal matrix. Once again we will just do a recap of this. You remember we did this orthogonal matrix in the case of QR decomposition. So we are going to say a matrix A is orthogonal matrix if number 1 AI dot AJ is equal to 0 if I is not equal to j, and is equal to 1 when I is equal to j, where AI and AJ are the columns of A. Is that okay? Now what we are going to do is we are going to actually prove. We just took that real symmetric matrix, we saw by an example that the vectors are orthogonal to each other, but we are going to prove it is indeed that if you have real symmetric matrix with distinct eigenvalues, the eigenvectors corresponding to these distinct eigenvalues are going to be orthogonal to each other. So let us prove that. So let us take the statement. So what are we going to say? We are going to say that the eigenvectors corresponding to distinct eigenvalues of a real symmetric matrix are orthogonal to each other. Right. This is a very important property of real symmetric matrix with distinct eigenvalues, in the sense it actually helps us to choose a new basis for our column space, which is in terms of the orthogonal eigenvectors. So let us prove this. So let us prove that these two are actually the same. Okay, let us look at this. So let us consider this. Suppose A is a, I am just going to consider a 2 by 2 real symmetric matrix, and this is going to work with anything, I mean any higher dimension matrix also, if the matrix is real symmetric and has distinct eigenvalues. So we are going to prove this. Suppose A is a 2 by 2 real symmetric matrix is a 2 by 2 real symmetric matrix with distinct eigenvalues. say lambda 1 and lambda 2 eigenvalues lambda 1 and lambda 2, then okay, okay. A is a 2 by 2 real symmetric matrix with distinct eigenvalues lambda 1 and lambda 2, and let's say u be the eigenvector associated with lambda 1 and V be the eigenvector associated with lambda 2. With lambda 2. We know that this distinct eigenvalues we have put lambda 1 and lambda 2. So, we know that A times u is equal to lambda 1 u and A times V is equal to lambda 2 times V, right. Now, we know that A is a real symmetric matrix. So, we saw since A is a real symmetric matrix, we have AU the whole transpose is nothing but lambda 1 u the whole transpose, which implies u transpose A transpose is equal to u transpose lambda 1, which is the same as lambda 1 u transpose, right. We have this. Now, what I am going to do is, and we know that A transpose is A. So, I am going to write this as u transpose A is equal to lambda 1 u transpose, yeah, because A transpose is A, right. So, let us take this as the first equation. Now, what I do is I am going to multiply both sides of 1 by the vector V. So, what are we going to do? We are going to get u transpose A V is equal to, I have lambda 1 and we had u transpose there, we had u transpose V. Is that correct? Now, similarly, so let us keep this as equation 2. Similarly, we can look at, we know that A V is equal to lambda 2 V. What I am going to do is I am going to do the same business that I did there. So, I am going to have let us do this. So, multiplying both sides both sides of, let us say, let us call this a star of star by U transpose pre-multiplying. So, what we have? We have U transpose AV is equal to U transpose lambda 2 V, which is nothing but U transpose AV is equal to lambda 2 U transpose V, right, lambda 2 U transpose V. And if you look at okay, let us mark this as equation 3. Now, we see that equation 2 and equation 3 have the same LHS, which implies I have lambda 1 U transpose V is equal to lambda 2 U transpose V. This is what we have, which implies I am going to have this as lambda 1 minus lambda 2 into U transpose V is equal to 0. That means this is what I am going to get. Now, there are two things that can happen here. This implies either U transpose V is equal to 0 or lambda 1 minus lambda 2 is equal to 0, right. But lambda 1 minus lambda 2 cannot be equal to 0, as lambda 1 is not equal to lambda 2. Why? Because we have taken lambda 1 lambda 2 distinct. Therefore, that implies U transpose V is equal to 0. What do we mean by that? U is the eigenvector corresponding to lambda 1 and V is the eigenvector corresponding to the eigenvalue lambda 2. So, we have U dot V is equal to 0, which implies the eigenvectors corresponding to distinct eigenvalues of a real symmetric matrix are orthogonal to each other. Right. Let us take a quick example of one more symmetric matrix and then see what happens. Let us take this example. A is equal to 1 0 0 0. Now, we see this is nothing but the matrix that projection matrix that projects every vector onto x1 axis, that projects every vector onto x1 axis. We know that this you take multiply, I mean you try to transform a vector x1 x2, the resultant is always going to be x1 0. Now, what are the eigenvalues for this? So, we have A minus lambda I, which is nothing but 1 minus lambda 0 0 minus lambda, the determinant of it is equal to 0. We have minus lambda into 1 minus lambda is equal to 0, which implies lambda into lambda minus 1 is equal to 0, which implies lambda is equal to 0 or lambda is equal to 1. Notice that the matrix A is a symmetric matrix, you have these two components to be the same. So, this matrix A is a symmetric matrix and we have distinct eigenvalues corresponding to lambda is equal to 0 and lambda is equal to 1, naturally we expect the eigenvectors to be orthogonal. Let us see what are the eigenvectors. So, lambda is equal to 0 implies we have this 1 minus 0 0 0 0 x 1 x 2 is equal to 0. So, which means I get x 1 is equal to 0 and 0 x 2 is equal to 0, which implies x 2 can be any scalar, any real scalar. That means the eigenvector corresponding to lambda is equal to 0 corresponding to lambda is equal to 0 is basically is k times the set of vectors, which is the set of vectors along the line passing through the origin in the direction of 0 comma 1, the vector 0 comma 1. Now, what does that mean? The eigen subspace, like what we saw, the eigen subspace corresponding to the lambda is equal to 0 is basically the entire x 2 axis, right. The entire x 2 axis is basically the eigen space corresponding to lambda is equal to 0. Now, the moment you know that in R2 I have one vector space which is basically the entire the line passing through the origin and in the direction of 0 1, that means the x 2 axis, I naturally know what is the orthogonal complement of it, or what is the vector space which is orthogonal to that, and that is going to be my x 1 axis. And it is also seen very clearly that any vector which is already on the x 1 axis, any along the line 1 comma 0 and passing through the origin and along the line 1 direction 1 comma 0, those vectors are already there, the multiples of this vector 1 comma 0, they are already there in the same direction. If you try to project it again, it is going to be there along the same direction only, which means the entire set of if you look at all the scalar multiples of this vector 1 comma 0, that is going to be your eigenvectors associated with the value lambda is equal to 1. Let us look at this. So, lambda is equal to 1 implies I have 1 minus 1 0 0 0 this is 0 minus 1 x 1 x 2 is equal to 0 0. So, we have 0 x 1 is equal to 0, which means x 1 can be any scalar, real scalar, and minus x 2 is equal to 0 implies x 2 is equal to 0. Therefore, the eigenvector is associated with lambda is equal to 1 let us say k times 1 0, and we see this 0 1 and 1 0 vectors are basically orthogonal to each other, and it is also interesting that they are orthonormal vectors in this case, right. And we see the matrix is already diagonalized, you have a diagonal form of this matrix. So, it is interesting to see that A is equal to 1 0 0 0. Here for this matrix the matrix corresponding to the the matrix which is populated with the eigenvectors, the P matrix is basically 1 0 0 1. The diagonal matrix is 1 0 0 0. P inverse, this is identity matrix, P inverse is also the identity matrix 1 0 0 1. Therefore, A you can very clearly see it is PDP inverse A is equal to 1 0 0 0 is the same as 1 0 0 1 into 1 0 0 0 into 1 0 0 1, right. So, this is what we have. So, what we have found is we have established that if you have real symmetric matrix, the eigenvectors corresponding to the distinct eigenvalues are orthogonal to each other. Now, what is the use of finding out or establishing this fact that eigenvectors corresponding to distinct eigenvalues of a real symmetric matrix are orthogonal to each other? Where are we, what are we going to do with that? We are going to see the effect of the matrix real symmetric matrix A on any vector, say u, or any vector, let us say x. We are going to look at the effect of this matrix A, real symmetric matrix A, real symmetric matrix with distinct eigenvalues on the matrix, on the vector, say let say some vector x. We are going to see how is this vector x getting transformed by this real symmetric matrix with distinct eigenvalues to another vector, let us say b, and that is what we are going to see, and that will be the focus of the next lecture, along with we are going to start we are going to get into the ideas of quadratic forms. So, we are going to look at both in the next lecture.